we're a few minutes in. Welcome, everybody. I'm Li-Ling Young. I'm an engineering consultant with Efficiency Vermont, and I'm really glad that you're joining us today. This is a topic that I have been working up for a while, and it's part of a series that I would like to tell you about. So I'll be presenting today with Bennett Doherty and Jamie Gerla. They're going to come in after I talk about my piece, which is coming right up. And we're also joined by Alex and Bryn from the Efficiency Excellence Network, which is our network of trade allies through Efficiency Vermont. So, as I said, this training is part of a series of trainings on quality HVAC. It's the first in the series. The second one is scheduled for next month. It's on heat pump installation and fast evacuations. It's going to be presented by Appion Tools, which is a manufacturer of high-performance HVAC tools. The third training is getting developed now. It'll be scheduled in April or May. So, I'm not really sure. And then there are going to be about 9 trainings in the whole series, so it'll go through the year. So I hope that you keep an eye on the EEN calendar and the EEN newsletter to see when those trainings are coming up. We also have our conference, the Better Building by Design conference, coming up in April, at the beginning of April. And there are several sessions there that are about heat pumps or relevant to HVAC designers and installers. The first one that's shown here is about the refrigerant phase down. So we have big change in the refrigerants that are allowed in new equipment coming up. And that is a session that I'll be presenting with my colleague, Melissa Stewart, and then Manual J, which is about calculating loads. There's a session on that. Supplemental heat is another session. This is supplemental heat for heat pumps. That's another session that I'll be presenting with another one of my colleagues. And there are more sessions that are relevant, of course. Going to the trade show where you can meet with manufacturers and learn about new equipment or even old equipment. The trade show is, I think, a very valuable part of the conference. So I hope that we see you all there. If you're part of the EEN, you get a benefit, a discounted attendance at the conference. So please come. All right, so here's our agenda today. I'm gonna start out by just sort of setting up why we're talking about what we're talking today by explaining what part load efficiency is. The core of what I'm gonna talk about is the NEAP database and a tool that the NEAP folks have put together to help with selecting heat pumps. Then we're going to move over to Jamie and Bennett's sections. They'll talk about some heat load calculators and some tips on how to do that for your projects. We're not going to take questions in the middle of all this, but after my section, we'll take a few questions if there's something that needs to be cleared up. And after Jamie's section, when he's talking about the heat load calculator that he's presenting, he'll take some questions. But we're hoping to leave some time at the end for all the questions and any discussion that you all might want to engage in. Let's see, before I get launched on this, I do want to say that if you're not part of the Efficiency Excellence Network, you can contact Alex or Bryn. You can also put a note in the chat that you would like someone to contact you about joining, because as I already mentioned, there's one benefit, which is a discounted attendance at our conference. But in addition to that, you have a relationship with one of the or more of the technical staff at Efficiency Vermont. And in the course of this presentation, you might discover that you feel like you want more close tutorial on how to use the tools that we're presenting. And you would be able to talk to an Efficiency Vermont person about that and have a one-on-one. And so that's a benefit, another benefit of being in the EEN. So please join us. All right, so what's part load efficiency? So this chart right here is showing two things. This long slope that starts high on the left and goes down to the right, that is the load of a building. I just picked a load. I think this is 35,000 BTUs an hour. And on the right side, the warm temperatures, the load is low, right? We don't need a lot of heat in a building when it's warm out. So the load, the amount of heat we have to add to the building to maintain the set point, that's low. Of course, when it's very mild out, there's no load at all. But as it gets colder, the load increases. And so each of these temperature slots right here, you can see what the load is by looking at the slope. I mean, this is a simplified version of it, right? Like it depends on if the wind is blowing and if the sun is shining, but nevertheless, that sloped line represents the load of a building. The other thing that this chart, and the orange vertical dotted line is the design temperature. So where the slope of the load intersects the design temperature, that's the design load for this building. The other thing that's being shown is these blue bars are showing the how much energy is consumed over the whole course of the season when it's that temperature. So at 35 degrees, you can see how high the bar is, and that is the BTUs that are required to heat the building whenever it's 35 degrees. And so those blue bars there, they show you the distribution of where we're using energy to heat our buildings. And that is entirely dependent on where the building is. So, sorry, got ahead of myself there. So the question of part load performance is really that part load means any time that we're not at those design conditions over here next to that orange bar. So part load could be a load of 80% of the design load. It could be at 50% or 30%. So it's really like all these other temperatures over here, aside from the design condition. And looking at the distribution of where the blue bars are, you can really see why it's important to understand what the heating system, or in this case, we're going to be talking about heat pumps, what the heat pumps are up to in these part load conditions, because look how much energy is being consumed in these part load conditions, right? So 20% of all of the energy that we use to heat our buildings is consumed at 40 degrees and warmer. So 40 degrees, like we hardly even think of that as being the heating season. And yet we spend so much time at 40 degrees and warmer over the course of a winter that accounts for 1/5 of all the heating energy that we use in the course of a heating season. I don't know if you would have anticipated this by looking at the chart, but half of all the energy that we use to heat our buildings occurs at 27 degrees and warmer. So 27 degrees, again, that's not, I think, what we all would consider cold weather. So a lot of the heating season happens at relatively mild conditions. And then if you look down closer to the design condition, which is in this case, it's -6 degrees, those BTUs, so the amount of energy we need to heat the building when it's colder than 0 degrees, that only amounts to 4% of all the energy we use in the season. So if you sort of think now about like what are we expecting our heat pumps to do, or what are we expecting our heating systems to do, right? They not only need to be able to keep us comfortable, but they need to be able to keep us comfortable during all of these conditions, when it's mild and when it's cold. And by doing that, we want it to be able to do that efficiently, particularly in the part of the season when we're going to use the most energy. Now, we already know that cold climate heat pumps lose efficiency and capacity when it's really cold. But look how many BTUs we're expending when it's really cold. Like, not that much. And so this area where we're using the most amount of energy, that's really important that we have our equipment operating well during those conditions. So this is what part load performance is. Part load efficiency is about how efficient our equipment is when we aren't at 0 degrees or -5 degrees or -20 degrees. All right, so now I'm going to introduce NEAP. And the CCASHP is the cold climate air source heat pump list, the NEAP cold climate air source heat pump list. So NEAP is an organization that works in the Northeast to support energy efficiency programs, and they have created a list of heat pumps that are suitable for use in the Northeast. So I'm showing here the main criterion for a heat pump to be added to our list. We all know that there are heat pumps out there that are really not suited for like a heating climate, right? And those are the heat pumps that were in use like 20 years ago. Everybody said, well, you can't use a heat pump in the north, and they stopped really creating heat at like 20 or 30 degrees. And that was true 20 years ago, but cold climate heat pumps are totally different. And how are you supposed to distinguish between the ones that really are not going to be good for this climate versus ones that are? Well, that's where the NEAP list comes in. And they created this specification for getting on the list. And what you're seeing in that table is basically, that's most of the specification. There's a few other little things, but it's about efficiency, right? So the HSPF is the seasonal efficiency. The COP is a point in time efficiency. So it's saying at 5 degrees, these different kinds of heat pumps, they need to at least be 175% efficient. That's what a COP of 1.75 means. And then SEER is a cooling efficiency. So the other thing that NEAP requires is that if you're going to be on the list, the manufacturer has to submit a form that has a bunch of data on it about the equipment, and it allows the NEAP list to have a very uniform presentation of the data about heat pumps. And it's really nice to have all these heat pumps together with the performance data all presented in the same way, because it makes it easy to compare between models. And this last bullet down at the bottom of the slide is saying that as part of submitting information to the NEAP list, the manufacturers are required to submit the capacity, so how much heat these heat pumps can push out, and the coefficient of performance, so that's the efficiency, at the, I'm going to skip that part, but at these temperatures. So at 5 degrees, what's the capacity? At 17 degrees, what's the capacity? And all these, up until the cooling side of things. So that is not information that was easy to find before the NEAP list. Manufacturers would hide that information in all kinds of different places, and they present it in different ways. And nobody really had published data at really cold temperatures. So this is where the NEAP list was just fantastic. It enabled us to compare models and to see how a model really would perform in colder weather. There's a little something missing in the NEAP specification, and we'll come back to that. And maybe you all are beginning to sort of wonder about that. Like, why is that it for the specification? We'll come back to that. All right, so this is how you get to the NEAP list. And Alex, if you wouldn't mind putting that link, I hope I sent you that link. If you could put that link in the chat so people have access to it. It's not hard to find the NEAP list, but this is where you get it. And now I'm going to try something a little bit difficult, just to switch my screen. What screen are you all seeing now?
We can see the website.
Great, thank you, Jamie. All right, so this is the NEAP list. NEAP does a lot of other things besides the heat pump list, so that's why there's all this stuff here, but I think mostly people use the NEAP website for the heat pump list, so they make it easy to find. And I'm going to click here. And this is the search page for the heat pump list. You can search in all kinds of different ways. Right here, it shows that you could search for like multi-zone duct lists, or you can search for single zone, mini split ductless style on the wall. You could just restrict it to ducted system, central ducted or compact ducted is like the mini split ducted style. So you can search by configuration. You can search by brand, right? And this is a long list here. You all might just think of heat pumps as being like Bosch and Fujitsu and Daikin, but look how long this list is. These are all manufacturers that have submitted equipment onto the cold climate air source heat pump. It's a lot. If you know the specific model you're looking for, you can put that right in here. And you might think, like, if I already know what the model is, why would I use the list? But remember that they have a depth of information on the heat pump list that is harder to find if you're just sifting through the manufacturer information. You can also restrict your search to a particular size. Now, in the work that I do, an 80,000 BTU an hour heat pump is like enormous. So I'm typically looking for stuff sort of down in the 10 to 20,000 BTU an hour range. So it's sometimes helpful for me to restrict my list just based on size. So I'm going to look for a heat pump here. I'm gonna say I want a ductless mini split. I'm gonna look for a Daikin. Just so you know, I just chose a random manufacturer. I'm not saying that Daikin is in any way better, but that's just one that made it easy for me to do the search. And I'm going to say over here that I want to see their products that are smaller than 20,000 BTUs an hour. So there's also this piece here, which is you can search just for Energy Star equipment, or you can search for things that are eligible for the tax credit. And this is really important to understand because I just talked about the specification again on the NEEP list, and it's all about efficiency. But the thing that the NEEP list doesn't include is a requirement that heat pumps have good capacity at cold temperature. They're just looking at efficiency. They're saying it at least 175% efficient at 5 degrees. But what if the capacity is dropped down to 10% of what it was, what the nominal capacity is? That for most people would not really seem like a suitable cold climate heat pump. But the federal tax credit does have a requirement for that. And so I have come to only consider equipment that meets the requirements for the federal tax credit as really being good heat pumps for use in Vermont. And even in Maine and New York and New Hampshire, Massachusetts. So I'm always clicking this box, and I encourage you to do that too. This restricts, like, there's something like 80,000 models in the NEEP list, and this cuts it down by like 2/3. So there's really a lot of stuff there that you would not want to specify ever. And by using this, you're really just looking at the stuff that not only is efficient at cold climates, but also maintains good capacity at cold temperatures. All right, so anyway, I have some criteria here. I'm going to search the list. So click that button there to search the list. And now remember, I just searched for Daikin, so that's why these are all Daikin here. But let's see, I'm gonna look for, now I searched for 0 to 20,000 BTUs an hour. And maybe that wasn't what I really wanted to do because there's a very specific model I'm looking for here. Hello, where's my 18? It's not here. All right, give me a second. Uh-oh. I knew this was going to get me in trouble trying to switch screens here. All right. I'm going to do a new search here. because I didn't find the exact model. Oh. Here's my problem. Sorry, people. I'm going to start again. And I'm going to search for my particular model that I'm looking for.
Hey, Lee Ling, do you want to just show people about clicking the cold climate button while you're there?
I don't know the cold climate button. What are you saying?
So on the left side where it says Energy
Oh,
Star
here.
certified, there's cold climate. So you want to click that and it'll just search only the cold climate.
You know, so my impression of what all these buttons amount to is that the tax credit thing includes everything that you would really want to sort for in the list. I don't think that the Energy Star cold climate certification is more stringent than the federal tax credit. So I'm only clicking this. You can also select this tax credit and this thing. Oh, look at that. It is more restrictive. Oh, I lost my heat pump that I was looking for. So I guess I understand what the tax credit requires. The tax credit requires that there has to be at least 70% of the rated capacity at 5 degrees. So that's pretty good capacity maintenance. I don't really know what's in the Energy Star specification, but evidently it is more restrictive than the tax credit specification. I think that the tax credit one is the most significant one. But you can also sort on the Energy Star. Okay, so here's my heat pump that I want to look at. And so this is the basic search result. On the left is just a whole bunch of information, you know, some numbers and efficiency numbers about the heat pump. But on the right here, the performance specification. I just want to check, are you all seeing my search results?
Yes.
Okay, thanks. All right, so on the right here, these performance specifications, this is showing you at different temperatures what the capacity is and the efficiency. And look right down here, fantastic. Cold weather performance, 5 degrees. It's showing you the minimum capacity, the maximum capacity, and the coefficient of performance, which again is the efficiency at this temperature. This is not a seasonal efficiency. It's just at 5 degrees, what's the efficiency? Okay, so that's really useful information. But there's also this little stealthy thing up here that doesn't even look like a button, but this is really where the magic happens. So this is advanced data. And this is what our presentation here is all about, is system sizing. So if you click that, you get this additional section here where you can put in information about your building, right? So now we have a database that's really all about heat pumps, but it gives you the ability to put in information about the building where it's going to go in. And we will see what happens as a result. So I'm just going to sort of make up a building here. If you put in the zip code, then you get these selections here of these different weather stations. And even though there's only 5, that's all you get to choose from in Vermont. So you have to sort of be savvy about where you're selecting your weather station. You just, you know, it's not necessarily the geographically closest one, but it's the one that feels like it's most representative of where your building is. Okay, so I'm just gonna say I'm in a relatively mild part of the state, so I'm selecting the Burlington weather station. The design temperature of Burlington is actually -6, so I'm going to change that. This is a ductless heat pump, and I'm not trying to meet the load of the whole building. I'm going to say that the load where I'm putting this heat pump is 12,000 BTUs an hour. So I'm going to put that in there. I'm going to ignore this cooling stuff because we're not going to talk about cooling loads today. And then oh, here, I almost forgot. So there's a little hidden thing here. If you click this, then you can put in more information. So if you recall, the coldest temperature that this heat pump has information about is 5 degrees. but I'm designing in an area where the design temperature is -6 degrees. And I know that it gets colder than that too. So I would really like to, um, to reflect that this heat pump does have capacity at colder than -5 degrees. And you can do this here by clicking the optional settings, and you'll see in a moment why this is important. So if I then click this box, I get a chance to put this in. And I happen to know that Daikin tests their equipment at -15 degrees. Now, the question is, where do you find this information? I did find it this is a submittal, and it's a long submittal, and it has like all of their ductless Arctic next gen sizes all in one single submittal. But anyway, different manufacturers hide this information in different places. It's worth it to track it down, and you'll see why in a second. So this is the model that we're looking at. Here's a table down here that shows that they have tested this equipment as low as -31 degrees. And I'm going to put in the 15-degree number. It's fine to put in any of these other really super cold numbers, but for my purposes, the 15-degree number is fine. So the maximum capacity is 16,000 BTUs an hour. Go back over here. 16,000, was it 480? That's right. Okay, so now I have all the information in here that I want to create this beautiful chart. So you might recognize this long slope line. That's the load of the building. This vertical orange line here is the design temperature, -6 degrees. That's the location where my building is. This yellow stuff is all new, right? So this yellow, I call it a cone. This yellow cone is the operational range of the heat pump. So this upper line here, the dark red line, that is the maximum capacity of the heat pump at all these different temperatures. The orange line down here is the minimum capacity at all those temperatures. And then there's a really unhelpful line in the middle, which is the rated capacity. I don't really care about that one, so I'm going to get rid of it. And then, of course, you recognize those blue bars in the back. We already talked about those. So what this is showing is that the load of the building is within the range of what the heat pump can provide for this long stretch here, right? So starting right here, the load of the building can be met by the what the heat pump capacity is, and it just modulates in order to meet that load. So it's not at high speed all the time, but it's higher than low speed. But what's happening over here, where the slope is a different color, is that the load of this space, I keep calling it a building, but it's really a space in a building. The load of this space is too low for the minimum capacity of this heat pump. And so what's going to happen here is that the heat pump is not going to modulate to meet that load. Instead, it's going to short cycle. And I hope you're remembering now back to my, what is part load efficiency, right? So this is the part load condition. This is not anywhere near our design conditions. And for a large part of these part load conditions, the equipment is not able to modulate. Instead, it's going to short cycle, and that does hurt efficiency. So we would expect to have poor efficiency all this range here, right up until this point, and then the heat pump can finally settle in and just run continuously to meet the load. So I'm looking over here and seeing there's a lot of extra capacity at my design conditions, and maybe this is not the right heat pump for this space. I don't want all this short cycling. It's going to hurt the efficiency. The building owner is going to pay more money. So maybe I should look at a different heat pump. All right. So I'm going to go back. Just a moment. I'm going to go back here and see if I can find a smaller heat pump. I like working with Daikin, so I'm still going to look for that same product lineup, but I'm looking for a smaller one. That was an 18. This is a 12. So I'm going to do this again so I can really narrow it down. There we go. That's the one I want. It's the same configuration, high wall ductless. Okay, so now let's look at this one. And you know, same search result kind of thing. I'm going to do the advanced data, get my weather stations, gotta fix the design temperature. You'll remember that my load was 12,000 BTUs an hour. Ooh, optional settings. I still need to do that. Oh, I didn't show you why the optional settings are important, but I'll show you on this one. So at minus 15 degrees, and then here I have, this is that 12 that I'm looking at, and my heating capacity, minus 15 degrees, is 13,900. Okay, so now let's look at what this smaller heat pump looks like. Maybe this will be better. Okay, so just so I don't forget again. So what would happen if I didn't put in this extra information about the performance at minus 15 degrees, the capacity at minus 15 degrees, is that this yellow wedge here would just end at 5 degrees. But what I'm showing here, because I put in that extra bit of information, is the yellow extends all the way out here to minus 15. And so it does give us the information we need right at the design conditions. Okay, so this is a smaller heat pump, and yeah, there's less capacity at minus 6 degrees, but this little wedge down here actually looks like there's still a lot of short cycling. And I think I can show you. Yeah, so this is the 18, right? And this is the 12. And they kind of look the same. So what I'm seeing is I chose a smaller heat pump, but it's still got this, you know, wedge down here where I would expect the heat pump is not performing very well. And in fact, it's like, this is 32 degrees where these two, you know, where the heat pump sort of crosses the load line, and we can start modulating. And this one is 30 degrees, which is like hardly any difference at all. And so it turns out that that we really need an even smaller one. And I'm going to spare you like me searching through it again, but this is the smallest heat pump in this lineup. It's the same Arctic Next Gen Daikin, and it's all the same design conditions, right? So here's my 12,000 BTUs an hour, and you know, all that's the same. And so this chart is showing this area, but below the minimum capacity of the heat pump. For one thing, it's a different color. It's yellow. And that's one of the things that the chart does, is it changes the color of that little wedge. If it's bad, it's red. And if it's good, it's green. This is yellow, so it's kind of in the middle. So to me, this is better because we have a much shorter part of the season when I'm short cycling. And you can see that down here. This is, so I just want to show you, this is the basic search results that that I showed at first, but these tables right here come in only after you make the chart. And so it's showing here that the minimum capacity threshold, so that's this little point right here, it's 40 degrees. And then on those other models, it was 30 and 32 degrees. So this is better. It's also showing over here what percent of the energy in the course of the heating season is going to be consumed under those short cycling conditions. And it's only 17%, 18%, which I consider to be acceptable. And then there's a bunch of other stuff here, which is really important, actually, like this supplemental heat number. And then here, this is showing you the load, like the energy load, how much energy is going to be consumed by the heat pump over the course of the year. And if you want help figuring out how to convert that to kilowatt hours, your Efficiency Vermont contact would be happy to help you with that. So that's a great way to get engaged with your technical consultants at Efficiency Vermont. Okay, so I think that this heat pump is a better application for my imaginary building that I'm designing for. However, look what happened up here. So this is in the coldest part of the season, and that yellow wedge now is not able to cover all of the heat load under the design conditions. So even though I'm like, oh, this looks like a winner because I have a lot less short cycling, the other thing that's happening is that I lost capacity. You know, it's just too small a heat pump to heat the space over here. And so if I choose this heat pump for this application, I'll need some kind of supplemental heat plan for the design conditions. And that happens to be one of my sessions that I'm giving at Better Building by Design. So if you want to know about supplemental heat and the impact on energy bills, come to Better Building by Design and learn about that. But what I want to say about this heat pump is sometimes it actually makes sense to undersize a heat pump, even though you might end up with the need for a little bit of supplemental heat. And the reason to do that is this section right here. You get much better performance at the part of the season when you're going to be consuming a lot of energy. You get much better efficiency here. And that would be a reason to undersize. Now remember, this over here is only 4% of all the energy that people are going to spend to heat this space. This is like 30% of all the energy. So you want good efficiency here. And in fact, we all expect good efficiency in warm temperatures, right? That's what the whole promise with heat pumps is like, you know, better efficiency when it's warm, we lose some efficiency when it's cold. But this is saying you don't always get good efficiency when it's warm out. All right, so let's see if I can switch back. Okay, now we're on our slide deck again. So I just want to repeat, there's a lot. Oh, I didn't even show you. Okay, so there's more to know about the cold climate heat pump. One of the things is it allows you to see charts. So that NEAP list will make charts for different equipment and allow you to look at them side by side. That's really nice. And another thing that it will do is it will show you it'll show you how you can meet the load of an entire building using multiple heat pumps. So if for instance, you have 2 or 3 single zone ductless heat pumps in a house, how the capacity of those stacks up to meet the whole load of the house. I'm not going to show you that now because that was a long time looking at a website. But if you want to know more about that, and if you want a one-on-one tutorial about using the NEAP visualization capabilities, that chart making capabilities, you can schedule an appointment with somebody at Efficiency Vermont to walk you through it if you're a member of the EEN. So join the EEN. I just realized like the sun is making me look like I have a mask on. This is just brutal this time of year in this room. Okay. So we're going to go on to the next section here. So this is all about selecting heat pumps. So use the NEAP list. And here's some things it can help with. One, it's really the only place that you can sort for equipment that meets the federal tax credit. And I talked about one way that it's important to select equipment that meets the federal tax credit, and that is that they have better capacity. Those heat pumps will have better capacity at cold temperatures. But the other reason to select heat pumps that earn the federal tax credit is because your customers might be able to claim that tax credit, and it's not an insignificant amount of money. So, really, you want to select equipment that's eligible for the federal tax credit. And I don't know any other place that you can sort models for that eligibility. The second thing you can use the NEAP list for is when you're integrating with an existing central fuel heating system, sometimes there's a question from the customers, how much residual fuel energy am I going to have to spend? And those charts, including that little table that I showed you underneath, will actually calculate that for you. You can also use the chart to size the heat pump if you know that you're customer will turn off the heat pump at say 20 degrees and they'll just use their oil boiler, then there's a way that you can use the chart to size the heat pump for that 20-degree mark, right? There's a feature there where you can say, we're going to lock out the heat pump at 20 degrees. And then all your sizing is at 20 degrees instead of at -6 degrees or minus whatever it is, the design condition in your space or your town. And then, as I said, it'll calculate how much energy the heat pump is going to use and how much energy the oil boiler is going to use. I mean, I think that's really clever. And if you all have an easy way to do that I don't know about, then let me know about it. But the NEEP list is a place that I think is really easy to get that information. And then finally, selecting equipment that has good part load efficiency. So you can minimize the low load cycling by creating that chart. It's not specific to the heat pump about how much low load cycling, short cycling is going to happen. It's specific to the combination of the heat pump and the building you're putting it in. So it's not always the case that there's like one heat pump that's like, oh, don't use that one, it has, bad part load performance. It depends on what building it is. So you have to create the chart to be able to see that. And to my mind, if you can keep it to less than 25%, then that's good. Okay, so this is, again, still about selecting heat pumps. So these are my tips. I think that there's probably more information than this to be had about good performance, selecting your heat pumps for good performance, but these are the things that I want to convey. I already mentioned this. Undersizing helps efficiency, and given how little heating is done in those super cold weather, sometimes it's fine to use something like even electric resistance heat to provide the supplemental heat at the cold end, because if you're going to get better efficiency at the warm end of things, the warm end of the season, in total, that's not going to result in higher energy bills. So consider undersizing if it helps efficiency. Use single zone models. And the reason for this is that multi-zone models do not come in small sizes. And I already showed you what can happen if your system is oversized. You get this bad part load performance. So if you have to choose a big one, like let's say the multi-zone that you're considering is 36,000 BTUs an hour, like that might be too big for what you need, but you're like, well, I needed 3 zones, so I had to get to 36. That's a setup for bad efficiency. So use single zones where possible, because they can be better sized to match the load. And a ducted heat pump. So if you do need to spread heat around to different parts of the building, a ducted heat pump is going to be better for getting heat into different rooms than a multi-zone, because a ducted heat pump, when it's heating, it has a bigger load that it can heat, right? So I don't know how to explain this. The slope of the line is different because it's not just trying to heat one room. All right, let's see. Okay, quality heat load application or calculations. So we're done with the NEEP stuff for now, and I just want to pause and see if there have been any questions, Alex, that you feel like should come in at this point.
Yeah, there was one we might have covered it, we might not have. Eric had a question, trying to find it in the chat. When you're talking about supplemental heat, he asked, "What if there's no supplemental heat? Would you have chosen the 12K?"
It fuzzed out right at the moment that you asked the question.
I've been having interviews this whole time. I apologize. Eric asked, "What if no supplemental heat? Would you have chosen the 12K?"
Oh, well, it really depends on what the building is. So it's very often the case, and I would love to hear from people in the chat about this. My question to you is, when you're selecting a heat pump, are you selecting a heat pump to heat like all winter long, or are your customers really asking you to provide heat for, like, let's say they have a wood stove and they only really need heat for, until it gets to like 20 degrees or maybe 10 degrees or 30 degrees, I don't know, like, or they don't have any other kind of heat and they're asking you to design a system that will just take care of all of the load in the building. right down to the, coldest temperatures, -10 degrees. I would like to hear from you. What are your customers asking for? So while I'm waiting for you to put your answers in the chat, I'll answer Eric's question. Eric, it really depends on what that customer wanted. So some people, we at Efficiency Vermont fully recognize this. Some people just want just want the air conditioning, and they might use their heat pump like a little bit in the fall, but basically they have a propane furnace and that's what they're going to use for most of the winter. So in that case, the question of supplemental heat is like, that's a non-question. They will turn on their furnace whenever they feel like they want, heat pushed out to every part of the building. So then that little supplemental thing, it's just a non-issue. If they have no other heating system and you as the designer are in a position of having to tell them like, this heat pump is not going to do the deal all winter long, so you need to have another plan. There are two things. I'm giving away like my entire presentation at BBD right now in the next sentence I give you. There are two things that I think are suitable supplemental heat for residences that are mostly heated with heat pumps. And one is electric resistance, and I already explained why. It doesn't really cost that much more money because it's such a small amount of heat and you get better efficiency on the warm side of things. And the other is a pellet stove. And I'm not going to say any more about that because I want you to come to my session at BBD at our big conference and hear why I think pellet stove is a good idea. So I hope that is satisfactory, Eric. And Alex, is that it for now?
Yep, I see some comments on, customer expectations and job expectations regarding heat pumps. I believe I do not see any questions. And as a friendly reminder, time check, it is 8:20 at the moment.
So does that mean that we are 50 minutes in?
Yes, I believe so.
Oh my goodness. I talked a lot longer than I thought. And we're going to 9 o'clock, right?
Yeah. Yep.
Okay. I'm going to speed along here. Okay. So quality heat load calculations. All right. So I'm just reminding you of this thing. This chart requires that load line. You cannot get any good information off this chart unless that load line is accurate. So that's what the next part of this is about creating that load. Okay, so what you need to know to calculate a load. And I just picked out the things that I think are the most important, and I think I'm right about this, but you'll be asked for a lot of information. Here's the things you really, really need to have correct. The surface area of the building. So you have to either measure the building or have a set of plans. The area of the windows and doors. Windows and doors are big heat losers. And so you really need to know like how much window and door area you have, because it varies a lot from building to building. You need to know the R values, which of course is the insulation in the walls and ceiling and whatnot, but you need to know the U values too. And that's the U value is the performance value for the windows and doors. The leakiness of the building. You have to have some way of approximating the leakiness of the building, or if you've had a blower door test done, then the leakiness of the building is actually been measured, and you can put that into the heat load calculation. And the design temperature of the location where you are. I'm going to skip that bottom part there and show you this, design temperatures. These are the official design temperatures in Vermont. Do not override this. This is recorded. If you need to come back and find this, you can come back and find these numbers, but look at the counties where you typically work and just take on board that there are no places in Vermont where the design temperature is like -26 degrees, even though, sure, it has gone to -26 degrees in Vermont. These are design temperatures. They're not supposed to reflect like the worst case scenario ever in the history of the planet. Okay, so most of Vermont is like about, -4, -5, -6 degrees around there. This is the only county up here that's like, whoa, that is super cold up there. Okay, so what is ACA? ACA is a nationwide organization that writes standards, and these are, like, you can see that there's standards for residential and standards for commercial. We're not going to get into this, but I just want to tell you that ACA is kind of the official place where people say, like, did you do good design work? than if you did according to ACCA. And we'll come back to that when Jamie and Bennett talk about their load calculators. So we evaluated a bunch of load calculators, more than what's on the page here. And in the end, we felt like we wanted to present to you Better Built Northwest and CoolCalc. And you can see there that we, there were some things that we were looking for that was mostly like, is it going to be easy for people to use? All right. I'm actually going to skip this slide because I've been talking for so long, and just say that these are the two links and the load calculators that we're going to be looking at. And then I'm going to hand it over to Jamie. So Jamie, do you want to, I can stop sharing and then you share your screen?
Okay, that sounds good.
Okay.
All right, let's see if I can do this. It's been a while since I Zoomed for a webinar. All right.
While Jamie's doing that, Liling, we did have a quick question. I know, Bennett, you were addressing this in the chat, but Thomas asked if there is a standardized procedure for NEEP requirements from the manufacturers to submit NEEP data. And
yeah, there's a form. Let's see. Here's a link about LACE specifications. Yeah, so Bennett showed you the specifications, but there's also a form. So there's this, manufacturers have to fill out the same form. All the manufacturers are filling out the same form. Every model that the manufacturers submit, they have to fill out a form. And so this is the thing that's most valuable about the NEEP tool, the NEEP list, is that everybody submits their information to NEEP in the same form. And that makes it easy to compare one model to another. Okay, I'm going to stop talking, Jamie.
All right, can everybody see my screen? Great. And you can hear me. All right. So, yeah, as Liling said, we looked at a bunch of different heat load calculating apps. And I'm going to point out, my presentation is going to be on CoolCalc. I'm not going to actually jump live onto the software because that's asking for trouble. So I'm just going to do some screenshots and kind of talk you through how it works. So some of the general features of CoolCalc are, one of the best is it's ACCA Manual J approved. Okay, so that's very important. It's a cloud-based program, so you can use it on your smartphone or you can use it on your computer. It's always there, basically. You just log in. You can have multiple team members share the same projects. I found it really easy to use. There's a nice user guide on it. It leads you right through kind of the data entry. It's not like a big table that you have to go kind of figure out where you're going to put stuff in. It just kind of leads you through it. And it's also free for the most part. You can do everything and actually get through and actually have it spit out a bulk load heat load number for you. But if you want, and you can actually look at the report, but if you want to print it out or print out an official looking report, then you do need to pay $20 for 5, or you can, if you need more reports, you can get them in bigger bundles than that. All right, here's another link there. All right, so I'm just gonna go through kind of how you'd set up a project in CoolCalc. First off, this is kind of the home page and where you start at. On the left, you can kind of see there's kind of 4 main screens: project, construction details, dimensions, and HVAC systems. I'm going to start off in project. That pulls up this screen, and you basically put in, name your project and give it an address. One cool thing about CoolCalc is it pulls up a little Google map here, and you can actually, if you've got an existing house, you can pull that up, and that will actually help you with your data entry, and I'll talk about that in a second. All right, so it's got lots of automatic features built into it. One of the things is, Liling was just talking about design temperatures. It will automatically pull up the closest weather station that ACCA uses. And so it pulls in the heating design temperature of -4 and 85 degrees for this. Just as a reminder, as Leland said, these are not the most extreme temperatures. It's basically the 99%, the 99 percentile. All right. Oh, I forgot to show you. So the project I put in here, it's kind of, I put in my test house in Charlotte, and that's what we'll use for this, for modeling. All right, so there are two different types of load calculation. There's a block load where you get, it's basically the heat load for the whole house, and then there's a room by room calculation type. So there's two different ways. If you want to do the block loads recommended, as it says here, for existing homes where new ductwork is not being proposed. Room by room is recommended for new construction or when proposing new or modified ductwork. All right. So once you've gone through the kind of the project, project setup, you jump onto the construction details screen. And this has some basic information, like you put in the number of floors, square footage, the year built, the bedrooms. The year built is important because ToolCalc has some smarts in here that actually, it's going to use the code for that year to help do some of its modeling. All right, here's some of the dwelling info, some of this basic information. You know, above grade stories, number of bedrooms, and it's asking, does it have a conditioned basement? Does it have a conditioned space over a garage? Things like that. All right. Now, infiltration. This is a huge, very important, you know, part of modeling. There are two ways to enter the data in. Well, I should say there's a big option here. So it's going to ask you, was a blower door test performed? Oh, I should just mention that anything I have circled in a big black box, that's an actual screen clip from the program. My questions and commentary is on the left side of your screen. So it's going to ask you, was a blower door test performed? If you say yes, and you have an ELA, which is the, oh my gosh, Leland, what is that? I know it's like equivalent, a leak area there. I think I got it right. So that's like the equivalent hole size that you have in your house. And I've got the tip right there here that says divide. If you've got a CFM 50 number, you can just divide by 8.2, and that will give you your ELA number. So you can enter that in there. And if you want to adjust the wind velocity, things like that, you can enter that in there. If you don't have a blower door test, then you of course click no, and you can put in this kind of qualitative measure. This is a pull down screen on the right, and you can select tight, semi-tight, average, semi-loose, or loose. You're probably wondering, well, what is that? You know, how does that correspond if, you know, in the real world? I don't know what semi-tight actually means. I found this on the Manual J manual that this is the corresponding air changes per hour that those kind of qualitative terms refer to. All right. Next, you go into the construction profile tab, and you enter in some kind of general envelope details. You know, what kind of wall is a frame wall? It's made out of wood. Kind of siding. What your ceiling insulation is like, and a few other details here. All right, so the next tab is the construction features group. And what this is really doing is you're going to spend a little time here kind of setting up your catalog of the different wall types you have in the house, the different ceiling types. You know, do you have a flat attic with, you know, R49? Do you have a section of slope roof? What are the different window types you have in the house? So you kind of set up these different, you're setting up your catalog Okay, you're not going to put any of the dimensions of these, like the size of the walls or the windows. You're going to do that later, but you basically set up this catalog. So this shows here on the right that for the above grade walls, I'm putting in, here's one type of wall I put in, a frame wall with wood framing. And if I click, well, I'll show you in a second, but let me just go ahead and click this. Okay, so this shows a detail of that wall. So showing it's wood, it's 2x4, it's R11. There's no board insulation used, and it's stucco siding. If I've got several different types of walls, I would input each of these. So maybe I've got a 2x6 part of my house. I'd enter that in, and I do the same for the floors and ceilings for all the different types. All right. Defining windows and doors, you're going to do the same thing. In the windows, it allows you to put in U values and your solar heat gain numbers. But for doors, it does not allow you to put in U values. If you've got a door that's got, I think, more than 40%, it's a 25 or 40, I'm forgetting now, but it's of window area, it's going to ask you to basically model that as a window, as a French door or sliding glass door. All right, so I'm showing you my showing you the catalog of window types that I've set up. I've set up some of my main windows here. I've set up a glass door, and I've got some cheaper basement windows that maybe they're much lower or much higher, a poorer U value. Okay, now dimensions. This is now, I'm down on my third big kind of tab, and this is where I get into the nitty gritty and really put the house together. I'm going to be pulling up from my catalog the different types of structures, wall types, and whatever, and I'm going to be adding dimensions to them. You can see here that on the right side, oops, on the right side here, it's showing kind of the different type parts of the house: basement, first floor, and second floor. Right now, it doesn't show any rooms for the first and second floor because I haven't added it. All right. Now, there's two ways to add dimensions in CoolCalc, which is it's kind of cool. No pun intended. If your house is an existing house, as I mentioned, it's got Google Map kind of built into it, and you can pull up a satellite view of that existing house, and you can just trace this, and draw in your rectangle, and it'll give you the dimensions of that footprint. So that's called the map trace mode. If it's a new construction, you don't have this, it's not going to come up on satellite view, then click the text entry mode. All right, map trace. So I'm just going to show you a little bit of map trace mode. Once you outline the footprint, when you can click on each wall, and it will pull up a little window here for more information on the wall, showing here it's asking me, this is a basement I'm in right now, so it's asking me the average wall height above ground and below ground. And it's also asking for a kind of a qualitative window area. If you want to do a quick calculation, which is probably not quite as accurate, you can do this qualitative thing. So this is asking me, like, do I have like no windows on this wall? Do I have like, just a one small one, like maybe a basement window, or do I have like a few average size windows, or the wall is all windows? So you can do kind of a quick calc by choosing that kind of qualitative area. I'm not going to go into a lot of detail here, but the center section here, I did try to find out what is actually meant by these low, medium, and high coverages. And I found these details as to what CoolCalc is actually kind of meaning for those. So if you want to look for that is here on this slide. All right. So, all right, we're running out of time here, so I'm gonna skip through some of this stuff here. You can, when you go into, for text-based, we're gonna go into text-based and show you just some sample screens of how to enter in data, all right? So, here, I'm basically entering in room dimensions. And on the right, it shows you the screen for that room, okay? And here you can, once you have your room selected, you can basically create walls, okay? So this shows a sample. You know, I've got a north-facing wall. I can put in type in its length. If it's got, you know, again, this qualitative number for windows, and the number of doors. If I wanted to get into more specifics on the windows, I would click the little pencil button, the edit button here, and I can add like more detail, exact measurements on windows, okay? All right, and you do the same for doors. A cool thing about this program is it actually allows you to put in internal loads. So these are like heat loads, you know, things that are generating heat or humidity in the room. So I can put in the number of plants. I can put in like, it's got a dryer in this room, it's got a clothes washer, it's got a refrigerator. You can pick and choose. It's really pretty easy to use and pretty powerful. All right, so this just shows so I'm adding rooms to each floor. The list on the right is showing all the rooms I've set up. I can click on any one of these rooms and it'll show me like the walls and all the details. All right, next and last, I'm going to the HVAC system. So basically, this is where I can choose like what kind of HVAC system I want to model. In this case, on the right, I'm going to choose ductless cold climate heat pumps. I can collect whether I'm heating and cooling. I'm clicking yes. Are all the rooms served by this heat pump? I'm saying no, because the basement in this case is not heated and it's a ductless system. So I go through here. Here's where I can pick. This screen shows how I can pick, you know, which rooms are heated and cooled. It allows me to put in some interior design conditions. So what people are basically going to choose for their thermostat settings, what kind of humidity they want in the house. It also allows me to put in what kind of, does it have a ventilation system in the house? I can choose that. All right, oops. So, all right, so this, I get to the big point that everybody's been waiting for. I can at last print out my MJ8, that stands for Manual J. I think version 8 is what the 8 is. And this, as I mentioned, this is an ACCA approved Manual J report. It's actually 19 pages long. So there's a lot of information in here. I'm just going to show you a few little pieces in this report. You got your main kind of pie chart showing where your heating loads are going to. You got it like a third of its windows. I got infiltration, above grade walls, ceiling doors. You know, that's shown in each of these pie charts. It's showing me various information on my fenestrations here on the right. Here it's showing component loads on the left side here for above grade walls, windows, all kinds of components. It'll do ceilings, all kinds of stuff. And then on the right, it's showing me, it'll show every room has a room detail showing the heat load and cooling load for that room, and some important graphs that I'm not going to explain right now. All right, more details. And you can put in various HVAC systems here and do quick comparisons for them. It's a really, I found it to be a real powerful program. All right, I've gone through kind of the most of the kind of the pros on this. I'll just say that the only kind of limitations I found is it doesn't necessarily go to real high insulation values. So if you've got a you know, a passive house or real high performance house, it may not have insulation values that go that high. It only goes to R56 in flat ceiling. And again, as I mentioned, the doors didn't allow you to put in U values. That's it for now. I'd be glad to answer questions, later or, text me. All right, Bennett, it's yours.
All right, awesome. Thanks, Jamie. I'm just gonna share my screen so that I can move that along. Just one sec. Oh, Jamie, do you mind? It's saying that I can't start sharing until you exit it.
All right, how do I exit? Stop share? Okay. Can you get it now?
Yes, I think so. Does that look good, Jamie?
Yes.
Okay, awesome. So thanks a bunch, Jamie, for walking through that. I'm gonna show one other tool, and we don't have a ton of time, and that's okay. I'm just gonna kind of put it out there just so you're aware of it as well. As Li-Ling said, we looked at a bunch of different ones. This is just another example of a free tool available. So this one's called the Better Built Northwest HVAC Sizing Tool. It was developed by the Northwest Energy Efficiency Alliance. Important to note, it's not an ACCA Manual J approved tool, but I still think it's worth knowing about just because it is free and easily accessible. And can be informative as well. So this one is web-based. I found that it was relatively fast to use, pretty easy to enter the data into, and you can print out free reports as well. One thing that's interesting, it does have a duct design feature. I'm not going to go into that today, but I think that that's a interesting value add to this as well. So I'll just give a kind of quick overview of it, and feel free to check it out more and ask questions about it as well. So I guess just so you all know, there's a login page. You can register for free. I'll move past that for now, but basically we have a sites page where you can see the your different sites, and if you click on new site, you can create a new house. And a lot of this entry is very similar to CoolCalc that Jamie presented. So I'll kind of go through this a little quickly, but one of the main things on this page is you can enter in that weather station, the weather location. And I'll show you in a sec too, you can edit the winter design and summer design temperatures within certain ranges as well. So the next tab, we move on to the building. And the kind of difference between CoolCalc here is that we have these tabs at the top and we kind of go across and enter them. Generally similar information, but it's just a slightly different process. And one important selection to note here is that you start out by entering a default installation level, and then you can do overrides after that. So this kind of gives you some defaults that adjust based on what you enter here, and then you can change things as you go. The next tab is the rooms, so we can enter room by room. I found this to be a pretty smooth way to just enter this information relatively quickly. You can enter in the floor area, the height, and whether it's conditioned or unconditioned above and below. And then comes the window section. One thing that is nice about this tool in comparison to CoolCalc is that you can enter the actual square footages of the windows in each orientation. And so this lets you do that relatively quickly. And one other thing that I'll note is that in the top right of this, there is a section that gives you kind of the heating and cooling load as it stands right now. This one's just you don't need to pay attention to it in this one, in these screens, but you can see it update as you enter this information, which is nice. So then comes the override section. So on the left side, you see all the default numbers that are entered based on the construction type that you put in. And then you can update these defaults with specifics in case you want to go with something different. A couple things to call out, and I like that it has some little informational tabs if you hover over them. You can enter a variety of U values for the or R values for the different assemblies, and it also lets you do some interesting things. So like input duct leakage, and it gives you some very specific information right here about what those different selections mean. And then importantly, Jamie talked about the infiltration number being important. This one I wanted to make sure to call out that this is the natural air changes per hour during the heating and cooling, and there's some details of how to calculate that from a blower door test from an ACH 50. But I'll move on for now. So then there's also this options page where you can update some of the other things. I look at this as kind of a similar override tab. Some of the things that I might just call out is you can adjust the design temperature. However, they do restrict it so that you can't say, you know, -30 or something like that. It does restrict it based on your range. So I think that's helpful. And then another thing that's kind of unique about this tool that I found is that it has an area where you can enter the ventilation rate if you have a ventilation system in the house. And I thought that was nice. It's maybe a small impact, but it is good to include. So a next step would be you pick out the system type. Since we're talking about heat pumps, I'll just show like you can pick out a heat pump, and let's say you select one. It does give you a graphic that's kind of similar to what Liling showed in the Neep tool. And one thing that is nice is that you can look at whether the design load is met. I think that the Neep tool has a lot more detail. So at this stage, once you have the load for the house, you might want to consider using that to like investigate different heat pumps because it provides a lot more detail. But one thing that is cool about this tool that's built in is that there's something called a heat pump manager. And if you click on that button, I'll just show you quickly here. You can enter in your own set points for heat pump. So they have some generic ones that come with the tool down at the bottom, but then you could also, I just entered something called brand and custom model. And then you, on the right side, you can enter the different temperatures and the capacities. And I just made some up there just so you can see. So I found this to be nice, maybe not as complete as the Neep tool allows for, but it is helpful that it's built into this tool as well. I mentioned before that there's a duct design section. I won't cover this here, but I think that this can be helpful for those that are interested in using this tool for figuring out some duct system sizing and layouts. So finally, there's the results tab. Similar to what Jamie showed with the reports in the CoolCalc, there's a section that summarizes your loads based on the different components, different parts of the house. And then if you scroll down a little bit more on that page, you can see the room by room loads, which is great. And that's how you can kind of assess different rooms, what the heating and cooling loads look like. You can print these reports out for free, and they include all of the inputs so you can see that all on one page. I also wanted to point out too that there is a YouTube tutorial section for this tool. If you go into that help tab, you click on the YouTube tutorial, it brings you to this page where you can see 4 different sessions that kind of walk through some of these things that I covered in a lot more detail. So if you're interested in using this tool, I'd encourage you to check those out. And I think finally, I'll just sum up that these are the 2 tools that we presented that are both free and accessible. Would encourage anybody that uses other tools to please chime in and share your thoughts, because we're trying to see what's working for people. How are you able to work HVAC sizing into your workflow? So if anybody has comments on that, would really appreciate that discussion. And there's also plenty of other great tools and paid tools like BrightSoft and Elite and things like that. But we just wanted to give a sampling of some of the things that are out there. And with that, I think I'll just open it up to questions. Feel free to ask questions about what we just showed. Also, if you have questions from the beginning about some of the Neep analysis that Liling showed, yeah, welcome any thoughts.
Thank you, Bennett. Thank you, Jamie. That was really a tour de force and brought us in right on time with some time for questions. So Chris, I see your question about the Fujitsu sizing tool. I haven't seen the Fujitsu sizing tool, but my opinion about all these load calculators is that the science behind how buildings lose heat is well understood. the math is not in question. It's not like these different tools are calculating heat gain and heat load differently. I think the biggest difference between all these tools is the user interface, whether or not you have to pay for them, and then the other features. So the Fujitsu sizing tool, I'm guessing, integrates really seamlessly with their Fujitsu catalog so that you can pull in a particular heat pump and then you can compare that heat pump performance to what your loads are. So that would be great if you use Fujitsu equipment and you're very specifically looking at how to, you know, how to match a particular building's loads with a particular piece of equipment. But we weren't able to look at the actual numerical loads that were generated by all these different tools and compare that. So I can't say for sure that they're not going to come up with different things for the load number, but I think the user interface is really the big difference. I also want to point out that Jamie's tool that he reviewed, which is ACCA approved, they're using ACCA assemblies that are in the manual, in Manual J, and you have to choose from those. Whereas the one that Bennett showed is not ACCA approved, and you can do a more customized assembly, and that alone could account for differences in loads. But what you have to give up for that flexibility is that you get a non-ACCA approved report.
Thank you, Jamie, Liling, and Bennett. That was a fantastic presentation. If anyone else has any other questions, feel free to put them in the chat. We have about 5 minutes to answer them. Additionally, this course is 1.5 AIA/Health Safety Wellness credits approved. If you or anyone else would like certificates of completion, please let Bryn or I know. You can reach out to us via email and we can get you a certificate of completion. And otherwise, yeah, we'll just take this time, and if you have any questions, feel free to ask them. Thank you.
Okay, so Brent is asking about Efficiency Vermont provides a tool called QLOS to anybody in the EEN. And again, if you want to know more about how to use QLOS, you can meet with somebody at Efficiency Vermont to walk you through that. The QLOS tool was originally designed as a way to compare, as a way to estimate energy savings if you made changes to a building. And over time, different features have been added to it, including it now will tell you what the load is in the building. It's not ACCA approved. It's just like open source spreadsheet. It's very easy to sort of screw it up by overwriting one of the calculations that's in the spreadsheet. But because it's not ACCA approved, it doesn't do things like account for internal gains and other little things that are in the manual. The tool that Bennett showed is more sophisticated than QLOS, and so it does account for many of those things, even though it's not ACCA approved. And so, as I said, we weren't able to model the same building in all these different tools and then come up with a uniform comparison of the results. But in general, QLOS is just less sophisticated than either of the tools that we showed today. What the tools we showed today are not going to do is they're not going to estimate savings. So while we're waiting for any more questions in the last couple of minutes here, I just want to repeat, we presented a lot of stuff today. And we all think that everything that we presented is really important to doing good design work. And when I say design work, I really mean selecting the equipment that's going to go in your buildings. It may be more than you're doing now. And if you feel like you want some help in figuring out how to effectively include this in your business model and the services that you provide to your customers, I encourage you to meet with somebody at Efficiency Vermont so that we can maybe take some of the struggle out of learning to use these design tools.
Looks like we have one more question in the chat here, Liling. Chuck asks, are the credits and incentives tied to a particular calculator?
No, at this point, none, the tax credit is not, doesn't require anything of what we have shown. The Efficiency Vermont incentives do not require this additional design work. No.
Okay. Well, looks like that is all for questions. And in 2 minutes, 1 minute early now. Thank you, Bennett, Lee Ling, and Jamie for making this time